Our aim for this lab was to carry out an experiment with the available materials that quantitatively demonstrated the law of conservation of energy. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time. This law means that energy can neither be created nor destroyed. Rather, it can only be transformed or transferred from one form to another. For instance, the total amount of stored chemical energy in a piece of wood would be exactly proportional at any point in time to the amount of energy released to the environment in the form of thermal, light, and sound energy when the wood undergoes combustion, plus the stored chemical energy remaining in the yet-to-be combusted wood. Likewise, the total amount of potential energy plus kinetic energy present in a closed system at an initial point is equal to the total amount of potential energy plus kinetic energy at the system's final point. This is the very situation that we demonstrated with our experiment in this lab. From the materials available in the lab, we chose to utilize a Hot Wheels track and car. With these, we set up a simple ramp as shown in this image. Our plan was to calculate the car's potential energy at the top of the ramp and then calculate the car's kinetic energy just before it hit the end point of the track to numerically demonstrate the conservation of energy. The height we used to calculate the car's potential energy at the top of the ramp was the distance between the car's center of mass when in the car start position and when in the car end position, the end position being just before the car hit the end of the track. This came to 0.46 meters, plus or minus 0.2 meters. The error was due to the accuracy of the ruler we used. The car was weighed using an electronic scale, and this came to 0.0323 kilograms, plus or minus 0.00005 kilograms, which is due to the accuracy of the scales we used. Using the formula, potential energy equals the mass of the object times the acceleration due to gravity times the vertical displacement between the object's start and end position, we found the car's potential energy when in the start position to be 0.1456 joules plus or minus 0.00848 joules. In order to calculate the car's kinetic energy at the car end position point, we needed to find its velocity at this point. To do this, we used Video Physics, a motion tracking phone app. This gave us a value for the car's velocity at the car end point position of 2.776 meters per second. Using the formula, kinetic energy equals half the object's mass times its velocity squared, we calculated the car's kinetic energy at the car end position point at 0.1245 joules, plus or minus 0.00197 joules. The two values, while close, are clearly not identical. After some discussion, we decided that this result should have been expected. As previously stated, the law of conservation of energy states that the total energy of an isolated system remains constant. However, our system was not isolated. While most of the car's potential energy was converted to kinetic energy, all of it was not. Some potential energy was lost due to the friction between the car's wheels and the track, the friction between the car's axle and the car's body, and air resistance, thus giving us a smaller value for kinetic energy than the initial potential energy. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time. To demonstrate this, we set up an experiment using a Hot Wheels car and track. We measured the car's potential energy while at the top of the track and then compared this to our measured figures for the car's kinetic energy just before the end of the track. Although our values for kinetic and potential energy did not exactly match as we initially hoped, we realized this was due to other forces acting on our system that we had not accounted for. Thank you.